So I want to just kind of preface the lecture with a thought experiment from the previous one. So, in the previous lecture, I spoke about particles diffusing in a random environment, and the setup was that all the particles started at the same location, and then they kind of spread over time. But in reality, you would never have all the particles at the exact same location, right? There would be some sort of profile that the particles would follow. And depending on the shape of that profile, it might affect the behavior of the extremes, right? The more spread out it is, the more the extremes would behave differently. So it's very interesting in that context to understand how changing the initial data changes the statistical behavior of the model over time. It's also interesting to understand what if you don't just look at the sort of maximal particle, but you look at particles that are pretty far along and how that changes. And so what this leads you to think about is the question of how does changing initial data and kind of changing where you're looking at a terminal time, what is the full picture? We kind of only looked at a very distinct thing. We looked kind of from a single starting point to somehow a single ending point. And I'd like to kind of step back and look at a bigger picture. So that's going to be the purpose of this lecture today. I will also address, I won't focus on that same model I spoke about on Tuesday, so this will really be disjoint. But in the random walk and random environment model, one of the shortcomings was that particles don't see each other, right? They see in a common environment, but they don't see each other. And so in today's lecture, we're going to look at the sort of completely opposite type of model, where there's a random environment and particles exclude each other. So they can't move through each other. They block each other. This is something called the asymmetric simple exclusion process. And so the methods that I'll describe here will in fact apply also to the model from the first lecture, at least the beta version of the model I spoke about. But I will focus on this other model in lecture 2 also to give you a flavor for it. OK, so the overall purpose of this second lecture is to extract what I'll call the sort of full space-time scaling limit. It's this. It's related to this picture I was saying, where you kind of are allowed to vary initial data in terminal locations and understand how that behaves. And the mathematical tool that I want to highlight is the Yang-Baxter equation and something called Gibbsian line ensemble. So these are both kind of hidden structures behind the models that we'll look at. I should say, because, we will get a lot. So in fact, we will really extract a complete picture, a complete scaling limit of the object. Of course, for many purposes, you want some much more marginal information, some sort of finite marginals. And then, of course, this will follow for free from what we're doing. OK, so here's the slide itself. This is joint works with various people who are depicted on the right. OK. Let me start with describing the model that I'll kind of be interested in for at least the first part of the talk, and then we'll go to a more discrete model. This is called the colored asymmetric simple exclusion process, and it's a model that was essentially introduced I don't know how many years ago that is, almost 50 years ago, or more than 50 years ago, I guess. If you've ever played, has anyone ever played this game before? Does that look familiar? I was given it as a birthday present by my aunt when I was young. This is a game where you kind of have the numbers 1 through 20, and you can make these sort of inversions, and you ask, how do you get from a disordered state to the ordered state of 1 through 20. So this game is not exactly the same as this, but it reminds me of it. So if you've ever played this, maybe this will remind you of it too. So the way that the model works is the following. So you have the line, the integer line, and every site can be occupied or is occupied by a particle. And the particles can have different colors. So here I'm using colors, and also I'm labeling the colors. So green, in this case, is the color 0. And red is the color 3, and so on and so forth. I'm going to start with some initial data. And in fact, for the time being, I'm going to start with a very special initial data, which is that at site I have particle minus I. So at site minus 3, I have particle color 3. At site 3, I have color minus 3. Okay? So it's a sort of, if you think of this as a permutation, it's like the completely reversed permutation is what I start with. Okay? And now the dynamics are as follows. It's a continuous time Markov process. And at every edge, so between any two sites, if I have a color j followed by a color I, you should think of j as being bigger than I. So say color 3 followed by a color 2. That switches to being ij at rate 1. And if I had the opposite, if I had ij, that would switch back to ji at rate q. That's it. This happens independently at every single edge and independent in time. Okay, so after some amount of time, for instance, you might have the 1 and the 0 swap. This happens at rate 1. And then, of course, it could swap back. And of course, because I'm imagining an infinite volume model, this is happening simultaneously, not simultaneously, but in any instant of time, there will be some amount of switching, but maybe it will be very far from the origin. Okay, so this is an interesting model. It's in fact even an interesting model if you restrict yourself to a finite region. One thing that is clear is that so I'm going to assume q is less than 1. So essentially the model wants to move more in the direction of being ordered. It starts completely out of order and wants to move towards order. In the infinite volume, it will never reach order, right? Because there's no way to go from the completely reverse ordered permutation to the other way. It takes infinite time. In a finite system, it could reach a completely ordered, the identity permutation. But in fact, as long as q is strictly bigger than 0, what will actually happen is it will converge to a stationary state on the order of these numbers. And it is itself an interesting thing. It's something called a Mallow's measure. You look at q to the number of inversions of your permutation. So imagine that there was no interaction, that I only had these 7 numbers and things couldn't move outside of this picture. And I ran it for a long time. I would see that the order of these numbers, the permutation I get, is the probability is proportional to q to the number of inversions of that. So even that is an interesting object. But we're going to be looking in the infinite volume setting where you're never going to be arriving at that stationary type of state. And this is just a convenience for later. I'm going to assume that time is being rescaled by 1 minus q. This helps for the statement of some results later. So here's one question. There are many questions that one can ask about this model, and I'll ask maybe 2. So the first question is, how does 0 behave? So just imagine that you only care about the 0 particle, and you want to know over time, what does it do? All right, so of course, here it moved left by 1. And now what happens? So there are some different forces that are occurring, right? Like on the one hand, all of these numbers that are bigger than 0 want to overpass 0, right? They have a bigger rate of switching with 0. So that would kind of lead you to believe that 0 gets pushed to the left, right? Bigger numbers want to go past smaller numbers according to these sort of stochastic rates. On the other hand, 0 is bigger than all of these numbers, and so 0 wants to overpass these numbers. So what does 0 do? Any guess? I'm imagining taking t to be very, very large, and I look at, say, the location of 0 at time t. I divide by t. That's a sort of, I look at the velocity that 0 establishes, and what do you think will happen? It's a diffusion, right? It will have velocity 0. And it will maybe behave like a Brownian motion under diffusive scaling, right? OK. So that's not the case. So what's shown here is a simulation of the trajectory of 0. So the colors here don't have anything to do with the colors here. Apology. This is the trajectory of 0 for, like, I don't know, 100 different simulations of the model, right? So you just keep rerunning the system. And what you see is that the trajectory that 0 takes, initially, it bounces around a little, and then it basically goes at a linear velocity. But the linear velocity is random. Okay? And in fact, you can prove, or we've proved, that it converges to this almost sure but random variable, and the random variable is uniformly distributed between -1 and 1. So in other words, the random velocity is somehow uniform on -1, 1. Okay. What's happening here is that you should really think of something like a reinforced system. An example being like Polya's urn, right? In Polya's urn, you have this notion of red and blue balls, and you kind of keep reinforcing. The more red balls you have relative to blue balls, the more likely you are to put in a red ball. So there's a bit of bouncing around that happens, and then eventually you stabilize. But you stabilize to something that depended in a non-trivial way on the early behavior, and that's what sets the randomness in motion. So kind of whatever you do early in life here, you get fixated on once you grow up a little bit. So the point of this is this is in fact not going to be the focus of my talk, but I wanted to illustrate to you that this model has many interesting features associated to it, and this is just one of them. Okay. Now the thing that I want to focus on in this talk is actually more related to random interfaces. So this is of course the title of the series. And that has to do with the fact that this model can be thought of as giving you an evolution of a sort of two-dimensional random interface, or a coupled set of one-dimensional random interfaces, which fall into this KPC universality class. So I want to explain how this works. Okay. So, if you think about the behavior of this system, notice that if I only care about colors that are bigger than or equal to 0 and then less than 0, all colors that are bigger than or equal to 0 kind of interact with each other in the same way. Like, okay, 2 and 3 can switch, but if I don't care about what's 2 or what's 3, I just care that they're bigger than 0, then I can just ignore that move. The only interaction that I need if I'm interested in this sort of brutal projection, where I only keep track of positive or negative, is whether what happens when a color bigger than or equal to 0 interacts with a color less than or equal to 0. And so what that corresponds to is that this model has nice Markovian projections. In other words, if I do this thing where I just replace all colors bigger than or equal to 0 by a black dot, I'll call that a particle, and everything less than 0 by a hole, a white dot, then this is in fact also a Markov process. And it's a simpler Markov process, which does the following. Particles jump right at rate 1, right? That corresponds to having had a bigger number, a black followed by a white. That happens and switches at rate 1. And the opposite occurs at rate q. Okay, so the opposite move occurs at rate q. Now, there's a nice encoding of this particle process, this sort of projected particle process, in terms of a height function. And the way that it works, and here again I'm assuming that I'm starting in this special initial data where I had the sort of packed or ordered configuration. I lost my cursor, whatever. So I basically start out with a step with a infinite number of particles and followed by an infinite sea of holes. And I can then keep track of the number of particles that are to the right of any location. So initially at time 0, there are, of course, no particles to the right of any location, starting off at the origin, moving to the right. So I have a height which I would call 0 there. I found it again. So I would start with the height 0, and then as I move over, yeah, that's much better. So then as I move over here, here I have exactly one particle sitting to the right, and so I have height 1, height 2, height 3, and so on. Okay. Now the dynamics of this ASAP means that when a particle jumps, it corresponds to the growth of this interface by the addition of a rhombus, right? Because, of course, the number of particles to the right everywhere else stays the same, except here, now I have exactly one particle that lies to my right, so my height needs to increase by 1 there. Okay? So the mechanism is very simple. It's that at rate 1, anytime that you have a little corner like this, so a down followed by a right step, it can become a right followed by a down step, the addition of a rhombus. And that happens at rate 1. And the reverse, when anytime I have a right step followed by a down step, I can remove that at rate q. Okay. So this projection has this very simple interpretation in terms of growing or receding fronts by adding these little rhombuses and removing the rhombuses. Okay. Now, on the other hand, this is only one projection of colored ASAP. And I could have done the same projection where I kept track of all particles that are bigger than or equal to 3 compared to all colors that are less than 3. And so I could have made my projection and started with a step that was, particle, 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 and then holes everywhere to the right. And so the colored ASAP, what it does is it couples together in the same probability space the evolution of these step initial data ASAPs from every potential location of the step. And I'll say a little bit more in a moment about what the nature of that coupling is, how to understand it in a very nice random environment sort of way. But before that, I want to state a result about this. Okay. So here, with that notion in mind, let me define, before I had a single height function, but of course I can choose the location of where I do my cutoff. So I'm going to define this h x, y, t as the number of particles that are of color bigger than or equal to x. So x is like the location where I made my sort of cutoff, that are to the right of y at time t. Okay? So if I had taken x to be 0, that was the picture from the previous slide. So initially, what does this function h look like? Well, depending on the value of x and y, either it's 0 or it increases linearly. Right? I'm just coupling together a bunch of these sort of creases, a bunch of these steps. Okay. Now, over time, what will happen is that each one of these step initial data, right? So I have all particles and then nothing. So think about how cars behave, right? The stoplight opens, cars start to kind of move, and there's a rarefaction that occurs. So there is a hydrodynamic limit that one has, and each one of these sort of step or creases will resolve itself to something that's a little bit more smooth. And so what you will have after some long amount of time is you'll still have a region which has slope 1, slope 0, and then there's some interpolation between the two. And this is a parabolic interpolation as dictated by the quadratic flux Hamilton-Jacobi equation that is describing that's describing the hydrodynamic limit here. Okay? So this is well understood, the sort of overall shape of this resolution of the crease. Where things get interesting is if you look at the fluctuations around that parabolic shape. And so for that, what you do is you use KPZ scaling. So you look as you vary both the x and the y. So the x has this role of the sort of color cutoff, or the location where your initial step occurred. And the y is the location at which you're observing this. And you allow each one of those to vary in the scale of of t to the 2/3. And then you subtract from that the overall deterministic parabolic shape here. And what's left over, you scale. So it's going to be large. It will live on a scale of t to the 1/3. T is big. So you're going to scale that back down to be of order 1. So divide by t to the 1/3. And what you'll see is actually a random two-dimensional surface. So what's being plotted here is the deviation of this height field. Here t is very large, and I've taken kind of a picture where everything is scaled proportional to t. And then I do this sort of mesoscopic scaling, and I look at the picture deviations around the curve, and it will look like this sort of interesting random two-dimensional height field. Okay? Now the dynamics of the colored ASAP gives me an evolution on that, and I'll talk about that evolution in just a moment. But I'm going to be right now just interested in what is this random two-dimensional surface. Okay? Of course, this two-dimensional surface contains a lot of information. It contains the information, if I just fix x and I look at the y variable, it contains the entire height function at some large time t, right? The fluctuations of that height function. If I fix y and I vary x, it contains kind of some other information. If I even just look at the one-point distribution, it contains interesting information as well. So here's what the theorem says. So I call this an ASAP TQ sheet. This is for any q between 0, including 0, and strictly less than 1. And what the result says is that as t goes to infinity, this random two-dimensional height field converges to a universal limit, something called the Airy sheet. And this doesn't depend on q. Yes?
I'm not sure I really understood what you're plotting. Is it spatial correlations?
No, this is literally the height function. So so I've run the simulation. All right, I have a way of recording based on the simulation. I have a way of defining a height function. And then I look at, I have a law of large numbers. I subtract that off. I look in a scale where x and y are like t to the 2/3. I scale the residual fluctuations around that parabolic limit by t to the 1/3. And I'm plotting what you get in terms of the fluctuations of the height function. And then I'm saying that this random field has a limit. And it doesn't depend on q. And I'll give a description of what this limit is. Yes? Q is the asymmetry parameter. It's the rate at which particles kind of backtrack, go the opposite direction to what you would hope. Yes?
Is the xy symmetry obvious, or?
No. No. You know, there are symmetries, and one can prove them, and the proofs are not trivial. They involve some Heck algebras or things of this flavor. But no. And in fact, well, I haven't said it, but this object is symmetric in x and y, this limit object. And there is some symmetry in the prelimit as well. Yeah. OK, so I'm going to digest this result and the implications of this result over the first part of the talk. And then, of course, we'll say something about how to prove this. And I haven't told you at all what this limiting object is, the Airy sheet. What? Does not depend on q. As long as I scale time by 1 minus q. So I need to be in units of 1 minus q. That somehow repairs an asymmetry, but it's an independent result. And in fact, this object should be the limit of any, well, OK, I'll give you some sense of any what. But this should be underlying the behavior of any sort of growth model or last passage percolation random metric model. Yeah.
I'm sorry, I'm kind of slow, but why are there, was there x and y, the height function only depends on one side?
So I'm looking at height functions for every choice of where I do my projection. So rather than projecting to call all particles to the left of here and all holes to the right, I could have done the projection here and said everything to the left is a particle, everything to the right is a hole. Each one would give me a perfectly well-defined projection, which is ASAP. And this gives me a coupling of all of those projections together on a common probability space. And I'm interested in understanding what the behavior is. Now you can ask why, who cares, right? Well, OK, maybe one cares about this model itself. But in just a moment, I'll explain to you that by actually understanding this model, you can understand much, much more. So this model, what we'll do in a moment is we'll actually embed this model in a slightly more complicated or simpler, depending on your background, model. And we'll see that, for instance, by virtue of this result, I'm able to tell you not just what happens for this special ordered initial data, but we can deduce what happens for any initial data for this model. So this becomes a kernel result from which all things follow. I can also, from this result, deduce what happens for the temporal evolution of this object. So maybe I'll show you a video. Find my mouse. There we go. So rather than looking at time t, I could look at time alpha t, right? And then I can think of taking t to infinity and then that was useless. And then varying alpha. We're going to get this to work. There we go. So this is the variation over time of that random height field. Okay, and you see, actually, it becomes a self-similar process. There's some scaling with respect to time for which, but it starts to flatten out over time. And I crashed it again. OK. Maybe somebody can come up and fix this while I keep talking. So OK, so what is it that I wanted to say next? I should try to remember. Yeah. OK, more questions while we wait for this technical issue. Well, OK, let me tell you where we're going to go with this. So the model, maybe the first thing I want to tell you is another place where this scaling limit, this what's called the airy sheet, arises. And while this is being fixed, maybe I'll do something on the board. There's chalk. Here we go. So you can imagine. Is this ready to go now? OK. OK. Perfect. OK, so this is another place where you should envision oh, there's some weird cutoff going on. Anyway, whatever. So this is another place where you can envision this airy sheet arising. So imagine that you have the two-dimensional lattice, but then you perturb the lengths of edges in some sort of IID manner, or some sort of short-range space-time manner. So you get, and you can't always draw this so nicely, but whatever. So each one, let's say the length is like an exponential random variable. Okay? And now you might want to know how long does it take to get from here to here. And there are various ways to ask that. You could ask for the minimal path, the maximal path. You could force that the paths kind of always take a step up or to the right, and then kind of restrict yourself from being able to do back loops. Any model of this sort is supposed to have some common scaling behavior. So the picture that's supposed to emerge is that if you allow the Euclidean length, let's say in this diagonal direction between the starting and the ending point, to be of order n, then this length is supposed to scale like a constant times n. The constant is completely inexplicit and model dependent. But then the fluctuations around that constant are supposed to live in an n to the 1/3 scale. And they're supposed to have this Tracy-Whittem GUE distribution modulo another constant that is also model dependent. So there is a sort of constant law of large numbers, and then there is a constant like rescaling of the Tracy-Whittem. And both of those are not easy to determine based on the microscopics of the model. But the fact that you have this scale of fluctuations and the limit is at least conjectured to be true. Now, from this perspective, you can also imagine what happens if I allow my starting point not to just be fixed here, but to vary in some scale. Right? So I think of a spatial scale as somehow this transversal direction. And I imagine my starting point varying in an n to the 2/3 window. So rather than being right here, I maybe allow it to kind of vary at a bunch of points along this. And I allow my ending point to also vary in some n to the 2/3 scale. Then you can ask kind of jointly under this scaling, what are these lengths, these sort of fluctuations of lengths? And the conjecture is that this should, and again, there will be one more non-universal constant that kind of scales this n to the 2/3 window, but it will converge to the airy sheet. So there's these two parameters, x and y. Now x has a very clear interpretation. It's the location of the starting point, and y is the location of the ending point. In the context of colored ASAP, it doesn't have quite as, x doesn't have quite the same symmetric interpretation as y, right? Y is definitely an ending point. X is kind of a starting point, but not really. It's like the location of the step. Okay? But there's, of course, one more dimension that we haven't really been playing with here, which is that there's the time dimension. So you could imagine not only varying the starting points in this scale, but also imagine varying the starting points in this order n scale along the diagonal. So there's really a two-parameter set of description of the starting point and a two-parameter description of the ending point. Now, when you're looking at this random metric model, it's very clear that if you know how to do it from a fixed starting point to another fixed ending point, as you vary the sort of spatial direction, then you can actually compose those. They form almost fundamental solutions, right? If I want to know the passage time from here to here, I should just draw a line across, and compute from here to every point along that line, and then from every point along that line to the end, and do a variational problem. So you can build up from this 2-parameter field a more robust object, which is this 4-parameter object, something called the directed landscape. Now, I should say in the context of these random metrics, there's a few models for which this has been proved, starting with work of DeVerne, Orthman, and Virag. But the general results quite open. OK, so with this in mind, I want to describe to you where, and I don't know where the title has gone, but where this sort of 4-parameter object is going to live. Remember, again, I can kind of start varying the starting time and location and varying the ending time and location in the directed metric model. So where is that picture going to be here? And this will bring me into what's called the basic coupling, or the graphical construction, or a sort of dynamical system approach to understanding this colored ASAP. Okay, so what is being depicted here? So one of the ways, and this goes back to the 1970s, one of the ways that you can imagine constructing or simulating this asymmetric simple exclusion process is by introducing a random environment and then a deterministic evolution in that environment. So what is the nature of the environment? So you have, again, time is vertical, space is horizontal. And between every pair of neighboring sites, you have a Poisson process of left and right going arrows. Okay? The left going arrows occur at rate 1. Is that right? No. The right going arrows occur at rate 1, and the left going arrows occur at rate q. So you should think of these arrows as defining a random environment. Just a bunch of arrows. That's it. And now what happens in that is once the arrows are fixed, you can specify at some time that you're going to kind of probe the system by particles. So you insert particles in. Let's say you insert a step, a bunch of particles, and then no particles. And you just let the particles follow the arrows. So in other words, particles stay put. They move vertically, except if they encounter an arrow, they follow the arrow. And the only rule is that if they follow the arrow into a site that's occupied, they don't do it. So there's exclusion. So you try to follow the arrows, and if the site is occupied, you just continue going straight up.
And if you have 2 arrows on left.
So because this is Poisson, you'll never have 2 arrows at the same time. Yeah. Right. So this is kind of the saving grace from needing to break the tie. There are discrete time versions of the model, in fact, we'll introduce a little bit later, where you need to contend with that, and then there are some specific rules that you use. OK. So that's the evolution. Okay. And now you can imagine probing this random environment and asking how does it respond to different probes. So what does it mean to probe it? It means that you put in some initial data at some time, and then you ask how does that evolve. And so there's really a solution map, right? Initial data comma time maps to evolution of that initial data over time. And what we'd really like to understand is what is the sort of full space-time scaling limit of that dynamical system, that random dynamical system. And maybe also we'd like to understand what the hell this has to do with the colored ASAP that I was just talking about. Okay? So in fact, and this is kind of one of the themes that I'm going to try to be getting across in this talk, is that you gain a lot by embedding complicated systems into more complicated systems. And so this is a more complicated, arguably, system than the colored ASAP. But we're going to embed colored ASAP into this, and then we're going to gain something, which is that we're going to be able to understand the full scaling limit of this object, which then, through projections, will bring us back to colored ASAP with, say, arbitrary initial data. OK, so let me describe something that is called, I don't know why the...
I just asked somebody should go to the...
OK. It's fine. It's just the title page. OK, so here we go. So this is a kind of a zoom-in version of the model. So you have all of these arrows, OK? And you see, here the particle would have wanted to go to the left, but it couldn't, because there was a particle here. Okay, and here this particle would have wanted to go to the right, but it can't because there's a particle here. Okay. So now you can ask what happens if I had a different initial data. So for instance, what if I didn't start with a particle here? If I didn't start with a particle here, then this particle actually could have moved to the left, and then it would have continued up. It still would have excluded this guy. And then up here, it actually could move back. And so the model, and you can convince yourself, has what's called the property being attractive. Okay, so it's a very good-looking model. No, what it means is that if you start with a system with some number of particles, and then you start with a system where at every site you have fewer particles, so in other words, you remove some of those particles, the evolution of the larger system contains the evolution of the smaller system. So here, the larger system had 5 particles. The smaller system had 4. I removed this one. And you see the defect, which I'm denoting by red, is actually a subset of the evolution of the original system. Okay? So this property is nice because what it means, in fact, if you think for a little while, it means that if you look jointly at the bigger system and the defect, it actually forms a colored ASAP. So if I look at these black particles and then the red, which is the defect, and then the holes, that actually forms a 3-particle ASAP in this colored ASAP. So and for that matter, I could have looked at, you know, a 5-particle system, a 4-particle system, a 3-particle, a 2-particle, 1, and I would have gotten a many-colored ASAP. Or for that matter, if I were to look at the step initial data, and then a step initial data where I changed the location of the starting point, and then I changed the location again, and I keep changing it. So I kind of keep shifting all of these steps, and I probe the evolution of them jointly in this random environment. That will be described by the colored ASAP. So in other words, the colored ASAP is describing a very particular marginal of this much larger system, where I probe it with these staggered steps at time 0. Now, what I want to argue now, or at least tell you, is that you should think of the location and the time at which your step starts. Right? There's no reason to only start steps at time 0. I could have also started a step. I could look at the evolution of a step at 0, and I could have looked at, inserting another step at some later time, and just asked kind of, how do each one of these steps evolve? So I can probe it in all of these ways. The probes are non-interacting in the sense that they interact through the fact that they're moving in this common environment, but I'm not thinking of these particles somehow interacting with these. I'm literally, I compute all of the arrows, and then I just ask, how do these particles evolve? And then I ask, well, if I put particles here, how do they evolve? And I'm going to describe to you that evolution. So before I had a height function that depended on 3 parameters, I insert a new one, which is s, which is the time at which I put my initial step in.
So Ivan, just one question. Yep. Do you still need the top of the screen, or is it getting better?
Oh, now it's better.
Okay.
Yeah, okay.
Yes.
It's back. Okay. Okay, so I look at the number of particles that are to the right of y at time t if I had started a step at position x at time s. So you should think of these steps as kind of they're going to be fundamental solutions in some sense, though they're in fact not fundamental solutions microscopically, but in the scaling limit they will form, they will converge to some sort of fundamental solution. So then what I do is I apply the same sort of renormalization operation. I scale the time s and t by order, say, epsilon inverse, x and y by epsilon to the minus 2/3. This is the typical KPZ 1, 2, 3 scaling. And I scale h by epsilon to the 1/3. And I, of course, do a centering by this parabolic limit shape that I had to deal with before as well. And now the theorem, in fact, it's a corollary of our earlier theorem. It says that as epsilon goes to 0, this renormalized 4-parameter height field converges to something that has a name. It's called the directed landscape. And it's an object that is built essentially in the prescription I was describing in the context of these directed random metrics. it's built out of independent increments of Airy sheets. So these Airy sheets were kind of what happens when you have a fixed starting and fixed ending time. And then I can compose those but through this simple composition law, which is the sort of metric composition law. And if I have independent increments that are these sort of rescaled Airy sheets, this is going to describe for me this scaling limit, this directed landscape. Okay. Now, this tells you, what this is telling you is that this 4-parameter object is somehow converging to this limiting kind of random fundamental solution for this KPZ universality class. The reason why this result is non-trivial is that this composition law, so we know already that the marginals from the theorem that I wrote down earlier, we know this sort of marginal convergence of Airy sheets. And from the fact that these Poisson arrows are independent over independent time increments, we know independent increments of the scaling limit. What we don't have pre-asymptotic is the composition law. We don't have the fact that if you start with a step at one location and then you kind of vary over some intermediate time, and then there's no version of this composition law which holds true for the model at a microscopic level. And so you need to prove that in the scaling limit you recover this. And this is what takes a little bit of work. OK, but once you've proved this result, we can actually kind of finally conclude maybe the biggest result of this, which is what happens for the entire dynamical system, right? So the whole dynamical system was start the system at any time with any initial data, any configuration of particles. It could be particle hole, it could be Bernoulli, it could be some weird profile of densities. Start it with any initial data at time s. Look at the evolution at time t at position y. So now think of this as a process in the initial data, which is some big dimensional, infinite dimensional space, in the time at which you set that initial data, and then at the terminal time. That object converges as a process to the solution to a variational problem where you basically take a Lagrangian, which is this directed landscape, and then you add, and sorry, there should be a parentheses x here. You add to it the initial data. So this is exactly what you would expect from the sort of metric picture. If you specify some initial data on some region, you want to vary over all paths that go to the region and sum it. So you end up with that picture for the scaling limit. And of course, from this, you can get anything you want. In particular, you could look, and this I should say is not just true for a fixed initial data. This is true simultaneously for all initial data. So this is a result that couples together over all initial data, over all time, over all y, over all t, and gives you a description of the scaling limit jointly. And so if you cared about some other initial data for colored ASAP, or you care about anything, one can extract that from this result. Okay? And I'll just mention that this right-hand side, if you fix a single initial data, there's actually a nice description of the sort of statistical properties, the transition probabilities, what's called the KPZ fixed point that goes back to Questel, Reminick, and Metetsky. And then but this, of course, gives you kind of a coupling of all of these sorts of objects. So in any case, it also proves that ASAP converges to this KPZ fixed point, which is a new result. OK, so hopefully I've given you some sense that you can get a lot out of this colored ASAP result. So there are many more things that I could say about results. I could talk about relations to what's called fluctuating hydrodynamic theory. There's some implications of this and behaviors of stationary measures. And I will touch on some of that in the next lecture. But what I want to do for the remaining half of the talk is I want to go back to the result that kind of underlies all of it, which was this scaling limit to the Airy sheet. And I want to tell you what the hell it means. Okay? So what is the Airy sheet, how you should think about it, and why it arises. Okay? So I want to kind of pivot now to talk a little bit more about the underlying mathematics behind this. But it will give you also an understanding of how you can extract information, right? Because at this point, I've only told you there is a limit, and the limit is something. I haven't really told you what to do with it or or how to think about it. So the message here, and in fact I already have given you this message in the first part of the talk, is that you can learn something by embedding a complicated system in a bigger complicated system. Sometimes it kind of unwinds the system a little bit. It helps resolve some of the complexity of the system. And so I want to start this second half of the talk by giving you a few examples of this. And I'll kind of build up from a almost trivial example to a much more relevant example. But actually, the trivial example will be quite informative. So this is the trivial example. Okay? So if you lost interest, come back. You'll learn something briefly. How do you integrate the sinc function, sine x over x, from minus infinity to infinity? All right. I remember first seeing this and having no idea how to do it. You know, okay, if you know complex analysis, there are tricks, right? But what do you do? So, okay, well, this is not a hard trick. This is just even. So, but now what you can do is, and this is something that is attributed to Feynman. I don't know if it goes back earlier. You can insert in a sort of integration factor, e to the minus tx. Now, if t is 0, this is the thing you want. So you want to know what this function h of 0 is. But now I've just made it harder, because I put in e to the minus tx, and I say, well, now I want to know this for all t. The thing is that I know what this is for a very special value of t, infinity. Right? If t is infinity, then this is just 0. And I know how to integrate 0. Okay, of course, you need to justify, you know, some interchange of limits. But so I know h of infinity is 0. And then I want to understand h of 0. So what I basically do, I put this factor in, and I look at another limit. So the other limit takes what's a highly oscillatory integral and makes it a highly localized integral, localized at 0. Now, what does this gain for me? Well, of course, I can differentiate in t. And when I do that, I clear the denominator. The x comes down, it clears this. And now I get a function that's purely exponentials. And I can integrate that. And I get the h prime is given by this rational function. And I can integrate that. And when I integrate that, I get an integration factor. So first of all, I get an arctan, and then an integration factor. But I know what h of infinity is, so I can compute the integration factor. And I get pi over 2. And now I plug in t as 0, and I get the answer, pi. Okay? So the idea here is not the specifics. The idea here is that you insert something in that makes it look harder. It adds a dimension. But then it allows you to transfer oscillations, oscillatory behavior, to localized behavior. And that's the idea that we're going to be utilizing in extracting the scaling limit of this model. Is we're going to embed the model in a larger, more complicated system. We're going to use a sort of integration factor, something that will transfer the behavior from one end to another end. This is going to be the Yang-Baxter equation. And then we're going to get something that is localized. It won't be quite as localized as integrating 0, but it will be something we can still extract the scaling limit of. OK. So let me now kind of ramp up the complexity and give you another example of where this concept of embedding comes in. And this is, of course, relevant for other subjects within this school. So you look at the random matrix theory. So look at the Gaussian unitary ensemble. So this is a 2x2 example. You have complex off-diagonal subject to Hermitian symmetry and real on-diagonal Gaussians. And if you look at the large n, so a large matrix, and you look at the eigenvalues, you see this Wigner semicircle and all these nice results about the bulk and the edge. And let's say that you only cared about the largest eigenvalue for some reason. Now, of course, it would be stupid for you to not know that these eigenvalues, that it's part of an ensemble of more, right? So, of course, there's benefit in not just looking at the largest eigenvalue. You look at the whole ensemble of eigenvalues. You have this sort of log gas, this expression given in terms of the Van Allen squared, and then this quadratic potential. And then by virtue of the Van Allen taking the form of a determinant, you're able to write this as a determinantal measure. And through various forms of asymptotic analysis, you're able to derive the Tracy-Whittem distribution for the largest eigenvalue. So this is not really a good example of my structure revealed through embedding, because why would you ever only look at the largest eigenvalue. You know it comes equipped with all the other eigenvalues. And so certainly you should use that. And this shows that it's valuable to use that information, right? But nevertheless, it's somewhat of that spirit. Now here's something where things become a little bit less, or maybe a little bit more interesting. Of course, you have this notion of Dyson-Brownian motion. So Dyson-Brownian motion involves replacing the static Gaussians by dynamic Gaussians, by Brownian motions. So if you replace all of these Gaussians by Brownian motions, now you get an evolution in time. And going back to Dyson, it was observed that this evolution on the eigenvalues is itself marginally Markov process, described by a stochastic differential equation. And that stochastic differential equation, which I won't write down, has the structure of its generator is the Laplacian on the Weyl chamber, the ordered locations lambda 1 through lambda n, conjugated by its ground state, which is the van der Rohe determinant. And because of that description, the evolution, so this is going to be the evolution over time horizontal, and each one of these, this is lambda 1 through lambda n. The evolution of the system actually has a description as n Brownian motions conditioned to start, let's say, all at 0, because I've assumed all the Brownian motions start at 0, and to never intersect. Okay, so that nice kind of ground state transform of a Dirichlet Laplacian translates into this nice sort of Gibbsian description of this as in terms of non-intersecting Brownian motions. Now you see we've gained something, which is that if I just looked at a single static time, I don't feel this Gibbs property, right? The Gibbs property says that if I look, let's say, at the top curve on some interval between A and B, maybe I even give a picture. Well, if I look on some interval at the top curve, that the law of, say, that top curve conditioned on everything else only depends on its starting and ending height and the location of the second curve, because it just needs to avoid the second curve, right? It was conditioned to avoid. And so you gain that dimension, you gain that extra property by going and adding this time dimension. And so from that, you can actually extract, well, I'd say from that and then the Carlin-McGregor formula, you can extract the scaling limit not just at a single slice of time, but you can look transversally in some window, say of width n to the 2/3 and height n to the 1/3 around the edge, and you can extract the scaling limit of the top k for arbitrary k curves, and this brings you to something that's called the Airy line ensemble. Okay, so the Airy line ensemble is describing the scaling limit of the edge of Dyson-Brownian motion under this KPZ scaling, and it inherits the Gibbs property, this non-intersecting Gibbs property that Dyson-Brownian motion had from its definition, which again says that if I condition on knowing the value here and the curve above and below, then the marginal distribution of the law inside is just that of a Brownian motion conditioned to avoid the above and below curves. That property is really useful. In fact, it's so useful that it defines the system. And I'll explain that in a little while. But the knowledge of the Gibbs property, the fact that you have a system with this Gibbs property and then some sort of parabolic shape is enough to uniquely define this object. And so you could imagine now that maybe you have some system of curves that you kind of don't have as much handle on as Dyson-Brownian motion, but you know there's some Gibbs property, and you know some sort of marginal information. Maybe the top one converges at a point. You might be able to then deduce the scaling limit of the whole ensemble using a uniqueness result, and then use that to deduce information not just about the top, but all of the curves and some arbitrary spatial interval. So that's something that we're going to do in a little while. OK, actually here I refer to this. So the strong characterization result of Agarwal and Huang says that any ensemble indexed by natural numbers, so the first, second, third, you have a natural number collection, index collection of curves. If the top curve has a general parabolic shape, so there's some sort of probabilistic statement of that sort, and you have the Gibbs property that I just described, then it is the Airy line ensemble. maybe up to some random height shift of the entire ensemble. And so if in addition you know at one point that it has the Tracy-Whittem GUE distribution, then it is the area line ensemble. There is only one such thing that has that property, and it is this. Okay? So that's going to be a very powerful result for us. We're going to be using this a little bit later. Okay. One last example before we get back to our ASAP. So remember we had this random metric type problem. We were interested in the scaling limit. And I said that there are some very special versions of this where you can actually do stuff. And so I'll describe to you one version of it and how one proceeds. So the model replaces the sort of space-time randomness of the deformation of a lattice by independent Brownian motions, or really independent white noises. And so the way it works is the following. You start off, let's say, at level 1 at some time. We'll call it 0 for the moment. And you consider a path that makes its way up and to the right and ends up at some terminal time tau and some height n. And the length of the path is given by taking the sum of the increments of Brownian motion. So for every level you have an independent Brownian motion, and you take the increment of the Brownian motion along the horizontal component of the path. Said otherwise, you can associate white noise to each horizontal, and you just integrate the white noise along the horizontal components of the path. So you eat up the white noise every time you're going on the horizontal. Okay, so it's kind of similar. It's not exactly the same, but it's a sort of a random environment, and you're kind of eating up noise through that random environment. Okay? Now, the thing that we were somehow interested in from the perspective of this random metric is what happens if you vary the starting point and you vary the ending point. What happens to the fluctuations of the maximal passage time, or minimal passage time, whatever metric you want. So here's how you go about studying that. So the first thing is that you're going to use something that's called the RSK correspondence. And I'm not going to go into any great depth on this, but what it basically says is the following. If I fix the starting point to be 0, I can plot, as I vary the location of the ending point, I can plot the length of the longest path. So I kind of vary this time tau, and I just compute, given my input, Brownian motions, what is the longest path? Okay? What's the length of the longest path? I plot that as the top curve over here. And then I can do something. I can look at the longest pair of paths that are non-intersecting. So rather than having one path, I could have a path that starts at 1 and 2, and a path that it ends at n and n minus 1. I guess the one that starts at 2 needs to end at n, and the one that starts at 1 needs to end at n minus 1. And I vary over all pairs of non-crossing paths the sum of their horizontal increments. And I get a number, and that number depends on tau. As I vary tau, I get different numbers. And if I take the difference between the top curve, which was the single path, and the pair of paths, that actually will give me the second curve over here. And then I can do that for a triple of non-crossing paths and minus the double, and I can get the third curve, and so on. And that's what, through what's a theorem of Green, that's what the RSK correspondence is. It's a mapping of whatever the random, whatever the functions are that you put on each one of these levels, it maps it to the longest one. The sum of the top two is the pair of non-crossing, of two non-crossing. That's sum of the top 3 curves is the triple of non-crossing, and so on and so forth. Okay. Now, the result, which is very important here, is that if you take a Brownian path, so you take the Brownian measure here, and you push it forward under this correspondence, you get Dyson-Brownian motion. Okay, that is not an obvious fact. This has to do with certain intertwinings of the generator and the behavior of the RSK correspondence, but it is a fact nonetheless. And so what that tells you is that if you wanted to know what is the what's the behavior as I vary my time tau of this last passage time, it actually is going to correspond to the fluctuations of the behavior of the top curve of Dyson-Brownian motion. Okay, so now we're already learning something, right? Like we knew how to do this Dyson-Brownian motion stuff. So we gain something here. We know what happens if you start at a fixed place and the ending point varies. You get the top curve of Dyson of this Airy in the limit of the Airy line ensemble. What if you vary the starting point too? So in that case, there's a nice combinatorial identity that goes back to Nomi-Yamada that says that, and again, this doesn't depend on things being Brownian. It says that if I start at a different location, let's say here, and I go to some ending location, then the maximum of the variational problem here in the environment given by these curves, whatever they were, is the same as the variational problem in this picture where I use the curves that are labeled, the first curve, the second curve, the curves of this push forward become the same as the curves that I thought, well, they become the curves that I'm using in my variational problem. So in other words, here I'm taking a variational problem through these curves, and here I take a variational problem through the curves that are recorded as the push forward under RSK. And Nomi-Yamada shows that this is an isometry. So in other words, all variational problems here push forward to or equal the solution of the variational problem here. So if I want to know what happens as I vary the starting time and the ending time, what I ought to do is vary the starting time and look as kind of a variational problem through this Dyson-Brownian motion and maximize all of the increments to my ending time. Now the thing that's cool here is that you see as you go into the bulk of Dyson-Brownian motion, things become more and more deterministic. Right? At the edge of a random matrix, there's a lot more randomness than in the bulk. There's a lot more rigidity in the bulk. And there's a lot more rigidity around time 0. So the variational problem that defines the sort of two-parameter starting and ending point object actually ends up converging to a variational problem that only depends on the randomness of the edge. In other words, a variational problem in the Airy line ensemble. So when you put it all together, you get, and this is what the work of de Vernhoff and Viereg did, you get that the scaling limit of this Brownian LPP as you vary the starting and ending point is given by a variational problem in the Airy line ensemble. So here, the thing that played the role of this sort of exponential factor, this e to the minus tx of Feynman, was this push forward under RSK. And you saw that the sort of, here a priori, everything depends on everything, right? There's like a bulk dependence on all of the randomness here. Here, it's only the randomness at the edge. Things somehow localized to the edge in terms of the fluctuations of the model. And from that, you're able to extract a scaling limit. So because you know this sort of marginal convergence of the edge, you get your full scaling limit. So I want to, let's see. So the rest of the talk, however long that be, I'm going to explain to you how you can do this for any model that's solvable by the Yang-Baxter equation. So to be clear, there is a very small set of models that are solvable by RSK, and there's a much larger set of models that are solvable by Yang-Baxter. And so I'll explain to you how the Yang-Baxter equation provides a mechanism for being able to prove convergence to the Airy sheet. The idea will be somewhat similar in the sort of overarching structure, but the role will now be played by Yang-Baxter, and of course the complexity of various limits will be much harder. Okay, so this was just to say maybe more concretely, this is what the Airy sheet ends up being, right? You have your ending location x and your somehow starting location y. You're looking at kind of maximal paths through the Airy sheet, and then I take this level to level k, I take k to infinity, and I kind of go at some sort of velocity, and this will converge to some object, which is this Airy sheet. So this is the sort of variational problem that one wants to arise at the limit. You see, it's a very probabilistic description. So if you want formulas, that's harder. But if you want kind of information, you can extract quite a lot of information because this Airy sheet, because the Airy line ensemble is a very well understood object. OK, so let's go back to what we're after. So this was the Airy sheet limit of colored ASAP. And the first thing that I'm going to do is tell you that I'm not going to actually work with colored ASAP. I'm going to work with a slightly simpler model or more discrete model, which is called the colored stochastic six-vertex model. Okay? Anything that can be done for this model can be transferred through a limit to colored ASAP. Okay? So what is the colored or uncolored stochastic six-vertex model? Let me start with the uncolored one. This is the analog of the particle and whole version of ASAP, just two types of particles. So what you have, and of course, this is some variant of the six-vertex model going back to Pauling, but it has this property of being stochastic that was really highlighted in work of Guo and Schmon. So there are 6 types of vertices. You have arrows that can come in horizontally and vertical, or no arrows that come in horizontally and vertical. And there's conservation of the number of arrows coming into a site and out of a site. So if you have 2 arrows coming in, nothing goes out. If 2 arrows come in, if 2 arrows go in, 2 arrows come out. If 2 nothings come in, 2 nothings go out. And then if something comes in from below, it can either cross through or it can turn. And the weight associated to each one of these pictures needs to sum to 1. And that's the stochasticity. And then if you go horizontally, you can either cross horizontally or turn, and the weights there need to sum to 1. So ultimately, this model has 2 parameters, right, because of this stochasticity condition. And so you can parameterize this in terms of what's called the quantum parameter Q and the spectral parameter Z. The choice of this parameterization is of course, very important. I'll tell you a bit about where this comes from in a little while. But let me first describe the model. So once you have these weights, you can now specify some sort of initial data. So you have the corner of Z2, so the quadrant, and you specify some collection of incoming arrows. Let's say you have incoming arrows on every horizontal and no incoming arrow on every vertical. Once you've specified that, you can use these weights recursively to sample the paths or the trajectories of these arrows. So you look here, you see I have a horizontal arrow and nothing coming in from below. And then I flip a coin according to either this probability or this probability, and I determine what happens to that arrow. So now it goes up. And now you see I've kind of constructed the system up to this point, and I can continue sampling. But here I have 2 arrows, so they need to deterministically cross through. So I recursively build up the system from the bottom left all the way up, and I fill up the whole quadrant. The important thing here is that this is different than the way that you would usually proceed with the 6-vertex model because of the stochasticity. In the usual 6-vertex model, you have a whole domain, so like a square in Z2. You specify boundary conditions on the entire boundary, and then you take the probability given according to the product of all of the weights normalized by some normalization constant. And the normalization constant is usually hard to compute. It's inexplicit. But here, because of stochasticity, all you need to do is specify the boundaries on 2 boundaries, and then the normalization constant is 1. And this allows you to progress and build the system up in a Markovian way. So this is what happens for this particular initial data. If you run it for some amount of time, you see the bottommost arrow somehow eventually kind of separates, not entirely. It kind of keeps bouncing around with the second bottommost and third bottommost. And then there's some region where there's only arrows and some region where there's no arrows, and then there's some sort of rarefaction fan between the 2. And in fact, you can prove a hydrodynamic limit for this model for looking at some slope and asking kind of macroscopically how many arrows are beneath it. And you can even prove a fluctuation limit. That's what we did here to the trace Uidum GUE. And this shouldn't come as such a surprise because the model is actually a precursor to ASAP. If you take this spectral parameter Z and you let it converge to 1, the model actually recovers ASAP in the following way. When Z goes to 1, the probability of going straight becomes 0, and the probability of going horizontal straight also goes to 0. But if you speed time up like 1 over 1 minus Z, then in that scale, the event that you kind of stay horizontal or vertical becomes a Poisson event. And so essentially what will happen is every particle will just zigzag to the right, up, right, up, right, up, right, up. Except on these Poisson times in this large time scale, you'll occasionally go 2 steps over or 2 steps up. And the relative ratio of these two weights is Q. Q is this asymmetry parameter, and this recovers a step. Okay, so the behavior of this model of uncolored stochastic 6 vertex exactly converges to the, well, in this case, step initial data ASEP for this initial data here. Okay. Now there's a colored version of this, which also has been studied. And here, it's actually, you only need to write 5 types of vertices because I and j are kind of now arbitrary, I less than j. And again, the picture is that if you have II coming in, then II goes out. And then if you have a smaller color crossing a bigger color, you have the option that they cross or that they kind of scatter off each other, and in the other I, j, you know, if I is going up, it can either scatter or it can cross as well. And you use the exact same rates. And so this is now what happens if you start the system with, say, all color 0 arrows, which I'm not even going to draw, and then color 1, 2, 3, this sort of rainbow type configuration. Then you end up with a system that, if I turned off all the colors, would look exactly like the picture from before. But now this keeps track of all of the colored of this colored ASEP. And of course, you can see if you track a single color, you see that they basically go at some linear velocities. This was like this ASEP. This was like the trajectory of 0 that we saw that takes some linear velocity. But all of these are coupled together in this system. And of course, you recover the colored ASEP in the scaling limit. Let me say very briefly about where this model comes from, or where these models come from. Okay, so why does one take this parameterization? What's the sort of origin of any of this sort of stuff, right? So essentially, the story goes, you go back 130 years to the world of circuitry. You have these Y delta moves in circuitry, right? You have these sort of, or star triangle transforms in terms of the effective resistances. And so there is some sort of understanding there that you can do transformations to electrical networks and not change the overall behavior of them. And so then if you kind of zoom forward to the Ising model in 1940s, Onsager, when he solved it, he also discovered that the Ising model has a sort of star triangle transformation that preserves the partition function. If you go a little bit further forward, people looked, so starting with Lieb, they were looking at a very simple version of this 6-vertex model where basically all the weights are 1. All the weights are 1. And what he observed, or others after him observed, is that you can write down the transfer matrices, and in fact, if you introduce inhomogeneities, you can write down and you can diagonalize the transfer matrices, and you see that the transfer matrices diagonalize in the same basis, provided that a certain relation holds on the parameters. And so that relation is that they have the same quantum parameter. So the thing that needs to be the same in order to have these transfer matrices commute is that this parameter Q needs to be the same. And then the Z, the spectral parameter, can differ. And yet you have the same basis. So once you have this, then it forces you to understand a good parameterization, right? Because you want to have some sort of parameterization where there's the parameter that needs to stay the same and then a thing that can vary. Then what happens in the story is that people understood, you have these commuting transfer matrices. They wanted to understand why they commute, not just by diagonalizing it, but how do you see it in a more kind of visceral way. And so the Yang-Baxter equation was actually introduced as a means to see why the transfer matrices commute. It's a sort of, there are these zipper arguments I'll give you an example of a little bit later, where you take, you have this Yang-Baxter relation, you kind of push it through, and it forces the commutation of your transfer matrices. And so that's kind of where the models come from. And then there became a whole industry of trying to understand, how do you use Yang-Baxter, or how do you find solutions to Yang-Baxter, and how do you make use of that? And that developed the whole theory of quantum groups and much more. Okay. So I need to be cognizant of the fact that my time is running low. And I think what I'm going to do is I'm going to give you a little bit more of this, and then I'll start the next talk and kind of finish the story, and then abbreviate the intended material from the third lecture. Okay, so we're trying to prove this theorem about colored ASEP, and I've now told you that we're actually going to focus on colored stochastic 6-vertex and prove a result there. And so now I'm going to, for the last few minutes, introduce the Yang-Baxter equation and kind of tell you how to think about it. And then in the beginning of the next lecture, I will tell you how we use the Yang-Baxter equation. Okay, so I think that will bring us to a reasonable time. So think of this as a primer on Yang-Baxter. Okay? If you've never seen this before, that's great, because I'm going to try to explain it to you carefully, what it means. Okay? So what's written here is the Yang-Baxter equation for the colored stochastic 6-vertex model. And in fact, let me even just for the, okay, I didn't do it in here. So let me explain to you how to think about this. So we have vertex weights, and they depend on Q. I'll think of Q as being fixed, and then they depend on Z. Z is the spectral parameter. And I'm going to allow Z to vary in a way that I'll describe. So now I'm going to restrict myself, let's say, to having n plus 1 different colors, so 0 through n as the different colors. And what I do is the following. I imagine specifying what the color is of all of the boundary edges. Right, so every edge in this picture has a color between 0 and n. And I can say maybe this has color 1, this has color 3, this has color 7. Now by conservation, whatever comes out here, here, and here needs to have collectively colors 1, 3, and 7. But maybe in some different order, right? So maybe this is 7, this is 1, and this is 3. Now once I've specified whatever the outgoing colors are, I have some potential choice of how they get rooted internally, right? Like, let me say for simplicity, just colors 0s and 1. So maybe I have a color 1, a color 0, and a color 1. And then maybe, maybe I should even draw this on a board, right? So imagine that I had, color 1 coming in, color 0, and then a color 1 coming in here. And then let's say I have some combination of colors coming out. I want to try to make this non-trivial, so let's see. OK, so imagine that this is like the boundary conditions of the model. OK, now what can happen is that the path can do what? So this can go up and then get reflected and then cross through. That's one way that I can kind of scatter these two particles to get the outcome. Or it could have gone over and behaved like this, right? So I could have, there are two different ways that together result in this sort of scattering process. Okay. Now, each one of these pictures has a weight associated to it. And what are the weights? Well, the weights of a picture is the product of the weights of the three vertices in the picture. Okay? Now, so there's this vertex, and this vertex, and I've drawn, because here I've kind of rotated it by 45 degrees. You see, this is like the horizontal, this is like the vertical. I have this little dotted curve, so you can match it up with the dotted curve here. It's just, you got to rotate yourself. Okay? So the x and the y here relate to the spectral parameters. You could even put a spectral parameter z here. And the rule is that the spectral parameter at a vertex is the ratio of the incoming horizontal to vertical spectral parameter. So if I had, let's say, a spectral parameter x, y, and z, which x, y, and z, what I need to do is here I use spectral parameter x over z. Here I use y over z. And here I use x over y. And once I know the spectral parameters, so that's I'm substituting that for what I had called z up here. I now can just compute the product of three factors from that table, add them to another three factors. And that gives me the left-hand side of the picture. Okay, so that is the partition function, and I should do that. I should consider that for every possible value of these external arrows, assignments of the external arrows, and of course I should think of then that as a function of x and y and z. You don't even need to, there is some sort of homogeneity, so you can think of z as 1 in this case. Now what Yang-Baxter says is that that needs to be equal to the same calculation if I switch the order of the scattering. So if I have, let's see if I draw it right. OK, so how can I go from this inputs, these 3 inputs, to these 3 outputs? What choice do I have? Well, in fact, I have no choice, because you see here I have, or do I have no choice? Let's see. So what can happen? So this can go over, and then this needs to go up. And oh no, so there are 2 terms. So, or it could go or this one could turn. And what Yang-Baxter says is that the sum of these 2 terms equals the sum of these 2 terms. So a solution to Yang-Baxter is an assignment of weights to vertices so that this equality holds true for all choices of boundary conditions and all choices of spectral parameters. Now you can imagine, of course, building up a more complicated version of the model where you don't just restrict your spaces to be 0, 1 or 0 through n. You could have more complicated objects that index your spaces. Right? It could be it could be triples of numbers or quadruples of numbers or arbitrary numbers of numbers. It could be even more complicated things like elements of some arbitrary set. So people search for solutions to Yang-Baxter under very much more general contexts, but we're looking at a very concrete example of this. Okay, and this is somehow one of the most basic solutions to Yang-Baxter. In fact, the case where n is 1 gives you really the most basic sort of solution. Now, I'm not going to tell you in this lecture because we're running out of time, but how we use Yang-Baxter. But what I want to close the lecture by is telling you how you can use Yang-Baxter to build up more complicated versions of Yang-Baxter. Okay, and that will be useful in the next part of the talk. Okay, so maybe I'll do 2 or 3 more slides and then end. So there's a process that's called fusion that goes back to the 80s, and the idea there is the following. So we had our basic solution. It's basic in the sense that I can ask, as a homework problem, check this. Okay, like it's not a hard thing. In fact, you just need to kind of keep track. Okay, you might say, well, I need to enumerate over all possible assignments. You'll convince yourself quickly that you just need to kind of look at the relative size of the numbers, right? So you don't really need to enumerate over lots of stuff. And in fact, most of the time, so at most you'll have is 2 terms in the sum on the left and 2 terms in the sum on the right. And most of the time you'll only have 1 term on each side, and then it's just trivial. So there are just a few cases that you need to check to confirm that this is true. Okay. Now what fusion does is it asks, well, what if I wanted to consider a system where I have not these sort of fermionic variables, where you can only have 1 arrow per site, but a more bosonic system where I can support more than 1 arrow per site. I have higher spin. So one way to do that is to compose these vertices in a specific way. So you could imagine the following. Imagine that you take, so each one of these can support 1 arrow. So I have some collection of arrows, I1 through IM. And I'm going to only do fusion in the horizontal direction right now. And I choose my spectral parameters in a very particular way. I choose them to be geometrically behaving as a function of q. So the parameter here is like q to the m minus 1, and then q to the m minus 2, and down to q to the 0. When I do this, what I do is I create a sort of a bigger vertex, one that takes in an m tuple of arrows and outputs an m tuple of arrows. So it's a transfer matrix. Okay? Now there's a very nice property of this transfer matrix, which I'm not going to check, but I'll tell you, which is that it preserves Q-exchangeable distributions on the order of arrows. What that means is that if I think of a measure on the initial collection, let me imagine all these are different colors. If I imagine a measure on the order of the initial arrows coming in, which is proportional to Q to the number of inversions, there's some linear ordering, so I keep track of the number of inversions of the permutation of the order versus where they show up. That's sort of Mallow's measure from before. Then that Q exchangeable measure, in other words, this Q to the number of inversions measure, gets pushed forward under the transfer matrix to a new measure, which is still Q exchangeable. So the transfer matrix, under the very special choice of spectral parameters, preserves Q exchangeability. What that means is that if I now imagine that I don't want to keep track of the locations of particles, of all of the arrows, but I only want to keep track of how many arrows there are of each color. So I kind of project from knowing the ordered list of 1, 0, 1, 0, 1, 1, 7 to just knowing that I had like 5 ones and some zeros and some sevens. If I sum out over, so if I fix the incoming I collection of arrows, and then I sum against this Q to the number of inversions, this Q exchangeability factor, multiply by this transfer matrix up here, and then sum out over, and then really project down to just keeping track of the outgoing arrows, this defines for me a new vertex, and that vertex solves, and I guess maybe I don't know, do I write this down? No. That vertex solves the Yang-Baxter equation, where now so here I've fused the vertical direction. So you should think of kind of a fused thick vertex in the vertical direction. And so I have here I use these L matrices, and then here still I use the R matrix of just the single colored, single arrow per site colored 6 vertex model. And this gives me a version of Yang-Baxter, which now involves a mixture of these L and R matrices. Okay. So the point of this is that from the simple solution to Yang-Baxter, we're able to build up more complicated solutions to Yang-Baxter. Okay. The proof of this is essentially a triviality. It just reduces to this, proving this Q exchangeability. It almost follows immediately once you do that. But then you get new parameters. So for instance, you can also do the fusion not just in the vertical direction, but in the horizontal, or not just horizontal, but also vertical direction. And then you can build up versions of Yang-Baxter where you have, L matrices, and then you have a higher spin matrix here that kind of takes how you fuse these two vertices together as well. And in terms of the models, in terms of the stochastic 6-vertex model, you can build up to what's called the colored fused stochastic 6-vertex model. And then through various limits, you have kind of 4 parameters, Q, Z, and then the 2 fusion parameters. You can do some analytic continuations and degenerations, and you get a whole zoo of different processes, for instance, that relate to things like the KPZ equation and other models, interesting polymer models and variants of. But this is, in fact, the model that I spoke about yesterday, this beta random walk in random environment model. You need to go up, and then you go down. And so anything that I can do here, all of the methods that I'm going to explain to you in the beginning of the next lecture for proving convergence of the entire space-time process for the colored stochastic 6-vertex model, all of that lifts here with some additional work, and then all of that degenerates down. And so the initial question I asked at the beginning of the talk can get resolved. It hasn't been resolved yet, but it can get resolved through the mechanisms. OK, so when we return tomorrow, the plan is that I'm going to tell you why this Yang-Baxter relation is important. It will play the role of this e to the minus tx factor of Feynman. It will allow me to transfer the complexity of the colored six-vertex model, colored stochastic six-vertex model, which kind of the height function depends on the entire bulk of the system. It will allow me to transfer that through to a more boundary-driven behavior. It will give me a relation to, ultimately, to this area line ensemble and this variational problem within the area line ensemble, which will eventually give us the area sheet. So I'll take the time that I need for that, and then depending on how we're doing with time, I'll spend a little bit of time talking about stationary measures and matrix product ansatz. Okay, thank you.
Thank you. Other questions?
Can you go back to the slide where there is the pictures with the from first and partial equations?
Yes.
So if you, my question is, if you want to prove this equality, you need to use the specific formulas you have for the weights.
So,
and again, is it equivalent that this commutation relation holds for this this formula for the weights?
yeah, so if you want to find a solution, so let me specify a well-posed question here, which is, if I fix the colors to be, say, 0 through n, and I fix that the vertices need to depend only on the relative, or the weight of vertices need to only depend on the relative order of colors, not on the absolute values of the, not on the actual values, but the relative orders. Then I will be forced into this solution. So this will be the only solution. In fact, a priori, there should be no solutions, right? Because there are so many constraints here, and there's very little freedom here. You have the freedom of, essentially, because of stochasticity, 2 parameters here. So here you have many, many equations, right? So a priori, there should be no solutions. But there are solutions, and that's kind of one of the beauties of this. Yeah. And as I said, the parameterization, it doesn't come out of nowhere, right? Like, there is a history for where this parameterization, how people realized this parameterization. They didn't just sit there and kind of, okay, this is a nice parameterization. Let me.
Yes. My question is about the directed landscape. I think, so because it basically contains all information that we can extract from the height function, I think it is an object that experimentalists like I want to evaluate. So I wonder if there is a practical way to numerically evaluate that object.
Yeah, this is a great question because, in principle, if you just care about a one-point distribution, you can plot a, if you care about, even if you care about the height function for step initial data as a random curve, it's really hard to check that a random curve empirically is another random curve that you have, you see a curve, prove it's Brownian, show that that is Brownian motion, right? Like, that's not a trivial thing. And of course, this is a more complicated object. So, the natural thing, of course, is to look at things like 2-point functions or 3-point functions. So there are things of that sort that you can certainly do. So one very concrete marginal that is not one that's really been studied before has to do with these fluctuating hydrodynamics. So what you can do, I don't think I have a slide for this here, but you can prepare a system of, say, colored ASAP at some density, say 1/2, and then a density which is like 1/2 plus some constant times epsilon to the 1/3, so slightly larger. And you can do it in such a way that they're kind of ordered. So maybe you use the same Bernoulli's, or you choose a uniform random variable and you just do a cutoff at 1/2 or a cutoff at 1/2 plus epsilon to the 1/3. And so you get these 2 coupled initial datas. Now, each one you expect to have this sort of marginal bike-Raines distribution for the 1-point distributions. But now you can look at some joint properties of them. You can look at kind of the 2, some correlation functions between the 2. And there are conjectures about the behavior of this correlation function and how it should be, what should happen. And you can prove these conjectures hold true using the directed landscape convergence result, or the area sheet convergence. So we do this in our paper, and we include then some results about this decoupling, and that's something that one could certainly check, and I think has been checked numerically for different types of systems. The only thing I'd say is that if you're truly experimental, if you're doing numerics, sure. If you're truly experimental, it's a little complicated to probe a system with two different initial datas, right? To probe the same system with two different initial datas. So, that's a challenge, right? Like what you could think of, for instance, in the context of my random walk-in random environment model is, imagine having two different types of microscopic particles, red ones and blue ones. And again, we kind of assume that they don't interact, but we could start one of the systems where the particles are all kind of here and another one where they're here, and then look at the evolution jointly. And they kind of evolve in the common system. So that's like one context in which you could imagine having multiple species.
So in the case of the airy line ensemble, as you explained, we can approximate it by Dyson-Brownian motion. So you can generate matrices large enough ones, and then you can approximate.
Yeah.
In the case of the directed polymer, something as direct is probably difficult.
You mean the directed landscape? Yeah. Or, yeah, well, you can construct it. There are ways to kind of build it out of independent Brownian motions as well, as kind of limits of independent Brownian motions. It's definitely harder, but so you can simulate it, right? Like in some sense, what I showed is a simulation of this airy sheet marginal. But again, trying to match that to experiments, you're looking at trying to match an infinite dimensional a distribution on an infinite dimensional object to something, and that's very hard. So you need to kind of reduce dimensionality in various ways. Yeah.
Okay, so there are no more questions, and let's thank again